So good day everyone. Today, we delve into the fascinating world beneath our feet, soil and sediments. So these often overlooked components of Earth's surface play a crucial role in supporting life and preserving our planet's history. So in this report, we will explore the types of soil and sediments, their texture and quality of analysis, cause of contamination, and natural synthetic way to remove contamination of soil. What are soil and sediments? Soil and sediments are integral components of the Earth's crust. Soil is a dynamic, living matrix composed of minerals, organic matter, water, and air. It serves as a medium for plant growth and plays a vital role in nutrient cycling. On the other hand, sediments consist of loose particles derived from the breakdown of rocks, shells, and other materials often deposited by wind, water, or ice. Formation process. Now, let's explore the intricate process that gives rise to soil and sediments. Soil formation or pedogenesis is a complex interplay of physical, chemical, and biological factors. The weathering of rocks, organic decay, and microbial activity contribute to the creation of soil over time. This process is influenced by climate, topography, parent material, organisms, and time that factors collectively known as CLORPT. As for sediment formation, it begins with the weathering of rocks to smaller particles. These particles are transported by various agents like rivers, wind, or glaciers. Deposition occurs when the transporting agents lose their energy, leading the settling of sediments in different environments such as riverbeds, lake bottoms, or ocean floors. So moving on to the types of soil and sediments, their texture and qualitative analysis. So firstly, we have sand. Granular substance made of finely divided mineral particles is called sand. Compared to silt, sand has coarser grains and is smaller than gravel. Next is shale. Shale is distinguished by its propensity to fracture into thin layers that are thinner than 1 centimeter. We refer to this quality as fissility. Next is sandy soil. Sandy soil is light, warm, dry, and tends to be acidic and low in nutrients. Sandy soils are often known as light soils due to their high proportion of sand. So, silt. The majority of granular material called silt, which is between sand and clay in size, is made up of fractured quartz grains. So silt can exist as soil or sediment suspended in water. Silt typically flees, flurry when it's dry, and rigid when it's moist. So next is loam. Loam is soil composed mostly of sand, silt, and a smaller amount of clay. By weight, its mineral composition is about 40 to 20% concentration of sand, silt, clay. Next up is alluvium. Alluvium is loose clay, silt, sand, or gravel that has been deposited by running water in a stream bed, on a floodplain in an alluvial fan or beach. Or in similar settings, alluvium is also sometimes called alluvial deposit. Alluvium is typically geologically young and is not consolidated into solid rock. Next up is clay. So clay is a type of fine-grained natural soil material containing clay minerals. So clay develops plasticity when wet, but can be hardened through firing. So lastly, we have limestone. The primary source of lime is limestone, a kind of carbonate sedimentary rock. The minerals calcite and aragonite, which are distinct crystals from CaCO3, make up with the majority of its composition. When these minerals separate from water, thus dissolve calcium, so it is limestone.
So now, what is soil and sediment pollution and how does it occur? Soil and sediment pollution occurs when harmful substances like toxic chemicals, salts, or radioactive materials accumulate in the soil. These pollutants have negative effects on both plant and animal health. As a universal sink, soil bears the greatest burden of environmental pollution, impacting the overall well-being of ecosystem and living organisms. The following are the different ways of how soils can be polluted. Soil pollution can result from various sources, including the pollutants from landfills, the release of industrial waste directly into the soil, the infiltration of contaminated water, the accidental rupture of underground storage tanks, the excessive use of pesticides, herbicides, or fertilizers, and lastly, the leakage of solid waste that degrades the quality of soil and sediments. As you can observe that these are mostly caused by human activities, emphasizing the need for responsible environmental practices to safeguard the health of our soil ecosystem. The most common chemicals involved in causing soil and sediment pollution are petroleum hydrocarbons. These are compounds found in crude oil and various petroleum products. Next is heavy metals. Metals like lead, mercury, cadmium, and arsenic, among others, are categorized as heavy metals. Next is pesticides. Agricultural practices often involve the use of pesticides to control pests. However, improper application, runoff, or leaching can lead to the presence of these chemical compounds in the soil. And lastly is solvents. Solvents are chemicals commonly used in industrial processes. Improper disposal, spills, or leaks can introduce solvents into the soil. When we talk about contaminants of soil and sediment, there are actually two types of it: inorganic and organic contaminants. The distinction between these two contaminants lies in their fundamental chemical composition and sources. Organic contaminants, composed of carbon-based molecules, encompasses substances like hydrocarbons from petroleum, pesticides, and various industrial chemicals. These contaminants often persist in the environment, posing challenges due to their longevity and potential bioaccumulation. On the other hand, inorganic contaminants are composed of elements and compounds without carbon-hydrogen bonds, including heavy metals and salts. These contaminants typically originate from industrial activities, just like mining in natural geological deposits. The behavior of inorganic contaminants depends on factors such as pH and microbial activity, influencing their persistence and potential impact on soil and sediment quality. So here are the list of common organic contaminants. First is polycyclic aromatic hydrocarbons, are a group of organic compounds composed of multiple fused aromatic rings. It is often produced during the incomplete combustion of organic materials such as coal, oil, gas, tobacco, and wood.
Next, we have nitroaromatics, which are a class of organic compounds that contains one or more nitro and O2 functional groups attached to an aromatic ring. Nitroaromatics are commonly produced through a chemical process called nitration. They are commonly found from a range of bactericides and pesticides to highly explosive materials commonly found in the military installations, such as TNT.
Next is phenols and anilines, originating from industrial processes like plastics and dye manufacturing. Phenols result from activities such as incomplete combustion and discharge from industries like pulp and paper mills. Anilines are prevalent in dye production, rubber, plastics, and pharmaceutical processes. So next is halogenated aromatics. These halogenated aromatics arises from industrial processes like pesticides, solvents, pharmaceuticals, and fire inhibitors. And let's proceed to halogenated aliphatic. These compounds serve as solvents in industrial processes, particularly when making plastics. It is also used in cleaning and degreasing agents. And next is pesticides. The primary source of pesticides is their use in agriculture to manage and prevent damage from pests such as insects, weeds, and fungi. So now let's proceed to the common inorganic contaminants. First is heavy metals. Heavy metals in soil and sediments have diverse sources, including industrial activities such as metal smelting, mining, agricultural practices involving fertilizers and pesticides, wastewater discharges from both municipal and industrial sources, atmospheric deposition from emissions, and natural processes like weathering and erosion. The nonmetals, on the other hand, comes from fertilizers, paper manufacturing, disinfection, or even aerospace. Next on the list are the organometallics. It has a role of being a catalysis and chemical synthesis, which is probably why its source comes from chemical manufacturing, just like paints. And lastly is radionuclides. Sources encompasses activities like nuclear power generation, nuclear weapon testing, medical application, and certain industrial and research processes. So those are the common examples of organic and inorganic contaminants. Now let's proceed to the solid and contaminant interaction. An important factor affecting bioavailability of contaminants is their interaction with solids in soil and sediments. First is association, retention, or sorption. In the context of soil and sediment, association, retention, and sorption collectively describe the processes which contaminants, particularly organic ones, form connections with solid particles. Association involves the bonding of contaminants to the surface of solid materials. Retention refers to the solid's ability to hold onto the contaminants, and sorption encompasses both these processes, representing the overall interaction where contaminants attach to or are absorbed by the solid matrix. This mechanism plays a pivotal role in determining the fate and behavior of contaminants in the environment. Next is adsorption. Adsorption in soil and sediment refers to the process where contaminants adhere to the surface of solid particles. It's like the contaminants sticking to or being attracted to the outer layer of the soil or sediment particles. Absorption. So proceeding to absorption. Absorption in soil and sediment interaction refers to the process where contaminants are taken up and incorporated into the internal structure of solid particles. It's like the contaminants gets absorbed or soaked into the solid material rather than just sticking to the surface. Next is partitioning. Partitioning in soil and sediment interaction refers to the distribution or allocation of contaminants between the solid phase and other environmental phases like water or air. It involves how contaminants move between these different compartments, impacting their overall behavior and fate in the environment. And lastly is precipitation. Precipitation in soil and sediment interaction refers to the process where contaminants react chemically with components in the soil or sediment, forming solid precipitates. This is akin to the contaminants combining with certain substances in the environment and settling out as solid particles.
Now we will delve into the technique of mitigating contamination of soil to improve environmental quality. What is soil and sediment remediation? Remember that previously we explored that contamination of soil and sediment arises from various sources, including human activities and natural contaminants. Soil and sediment remediation is a process of cleaning, restoring, or mitigating contamination of soil and sediment to improve environmental quality. The ultimate goal is to reduce contaminant concentrations to levels safe for both human health and in the environment. Remediation efforts can take various forms, employing both natural and engineered methods. Remediation methods can be broadly categorized into natural and synthetic approaches. The natural method utilizes organisms found in nature to fuel soil remediation. The synthetic method artificially treats the soil through various chemical or physical reactions. Each method is further divided into biological, chemical, and physical processes. Biological processes are natural methods, while chemical and physical processes are synthetic methods. There are two main remediation techniques, such as in situ, where the soil is treated without removal, combined with microorganisms or chemicals, and ex situ, involving the removal of soil for treatment. Each has its pros and cons, such as the effectiveness, cost, and environmental impact. The following diagram is an illustration of the different processes of remediation. The green triangle represents the soil in which the process uses. The yellow description on the bottom notes the disadvantage and advantages of each method. Next, we have added a flowchart of the soil remediation that identifies the process for both inorganic and organic contaminants. Lastly is a comparison of remediation techniques of in situ and ex situ. noting the effectiveness, cost, and environmental impact. Now let's look at the specific contaminants. Organic contaminants include hydrocarbons, polycyclic aromatic hydrocarbons, PAH, pesticides, and volatile organic compounds, VOCs. In the organic category, biological methods include in situ phytoremediation, where plants absorb contaminants, and bioremediation, using microorganisms to break down pollutants. Ex situ options like biopiles and bioreactors offer controlled conditions for microbial degradation. On the synthetic side, chemical methods include in situ options such as in situ chemical oxidation, ISCO, and in situ chemical reduction, ISCR. Ex situ options involve chemical oxidation reduction treatment piles. All chemical processes uses redox reactions to synthesize organic contaminants. Physical methods for organic contaminants include in situ techniques of soil vapor extraction, SVE, and thermal desorption, as well as ex situ techniques such as excavation and landfilling, and incineration. Here are a few example diagrams taken from different remediation processes for organic contaminants. Now we will look at inorganic contaminants, which encompasses heavy metals, metalloids, and salts. Inorganic contaminants lack the presence of carbon. Natural methods for inorganic contaminants include biological processes of in situ phytoremediation and ex situ bioleaching, using microorganisms to enhance leaching. Notice that phytoremediation can be used for both inorganic and organic contaminants. Synthetic methods for inorganic contaminants include chemical processes of in situ techniques such as stabilization and leaching. Ex situ techniques include chemical precipitation and solvent extraction. Physical processes for inorganic contaminants include in situ options of soil isolation and electrokinetic remediation. Ex situ options include vitrification and soil replacement. Here are a few example diagrams taken from different remediation processes for inorganic contaminants. In conclusion, soil and sediment remediation is a complex but vital process for preserving environmental health. The choice of method depends on the type and extent of contamination, site-specific conditions, and considerations of cost and sustainability. Understanding the various methods and techniques allow us to make informed decisions for a cleaner and safer future. Thank you for joining us on this journey through the world of sediments and soil.